Consider n real numbers x1, x2 to xn. The absolute value of their sum is 1, and each individual number in absolute value is less than or equal to n plus 1 divided by 2. Prove that there exists a permutation y1, y2 to yn of x1, x2 to xn such that the absolute value of y1 plus 2y2 plus up to n times yn is less than or equal to n plus 1 divided by 2. This is IMO 1997 problem number 3. It is a hard problem, but its solution is beautiful. First, let's introduce a notation for simplicity. Given any n numbers t1, t2 to tn, denote S of t1, t2 to tn to be a linear combination of the n numbers t1 plus 2 times t2 plus up to n times tn. We can simply call it weighted sum of the n numbers. There are two important observations. First, consider the original sequence x1, x2 to xn and its complete inverse xn, xn minus 1 down to x1. The addition of the two weighted sum, by definition, it is x1 plus 2x2 plus up to n times xn. This is the first sum, plus xn plus 2 times x minus 1 plus down to n times x1. This is the second sum. Combine the term, see all the coefficients for x1, x2 to xn are n plus 1. Take it out, and we also know the sum of the n numbers in absolute value here is 1. So we end up with n plus 1. This is clearly related to the target. We want to prove there exists a permutation so that its weighted sum in absolute value is less than or equal to n plus 1 divided by 2. Now, we have two weighted sum. Their sum in absolute value equals n plus 1. The problem is that we don't know these two sums are positive or negative. If one is positive and the other is negative, then their sum after cancellation equals n plus 1. Each individual one can still be larger in absolute value. We will deal with this later. Observation 2. We compare the weighted sum of two sequences x1, x2 to xn, the original sequence, and the other sequence is a permutation by switching two consecutive terms xk and xk plus 1. When we calculate their differences, all terms are cancelled except two terms in each sum. In the first sum, the coefficient for xk is k and k plus 1 for xk plus 1. And in the second sum, the coefficients are switched. This is equal to absolute value of xk plus 1 minus xk. That is less than the absolute value of xk plus 1 plus the absolute value of xk. But we know the absolute value of each individual terms is less than n plus 1 divided by 2. So the sum of these two terms is less than or equal to n plus 1. A quick summary. First, the addition of the weighted sums of a sequence and its complete inverse equals n plus 1. Secondly, the distance between the weighted sum of a sequence and a permutation by switching two consecutive terms cannot exceed n plus 1. These are all we need to complete the proof. Proof by contradiction. Assuming for any permutation y1, y2 to yn, the weighted sum of the permutation is strictly greater than n plus 1 divided by 2. Then, for all these weighted sums, they are either strictly less than negative n plus 1 divided by 2 in the negative area, or strictly greater than or equal to positive n plus 1 divided by 2, the positive area. There's no sums in between the big gap with distance n plus 1. Now, let's look at the weighted sum of the original sequence and the sequence by switching the first two terms. Clearly, these two sums are either both on the negative side or both on the positive side. They cannot be one on positive side and the other on the negative side, because by observation 2, their difference is less than or equal to n plus 1. The gap is simply too big. Now, x2 is the first term and x1 is the second. We can further switch x1 and x3 to move x1 to the third position. The resulting sum will still be on the same side. Repeat this process until the sequence is completely reversed. Then the sum of the original sequence and the reversed sequence must be on the same side. Then we have a contradiction. By assumption, the absolute values of these two weighted sums are all strictly greater than n plus 1 divided by 2. If they are of the same size, then their sum in absolute value must be strictly greater than n plus 1. This is inconsistent with the observation number 1. Thank you for watching.